Hello everyone, I am Abhinav and today we'll be discussing the fifth problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. So we would move on to our CP-31 sheet and we can see that the 1500 rating mark has been checked and we can see the clickable links to our problem. So let's move on to the fifth problem, which is tea tasting. Okay, let's read the problem statement, what it says. A tea manufacturer decided to conduct a massive tea tasting. N sorts of tea will be tasted by N tasters. Both the sorts of tea and the tasters are numbered 1 to N. The manufacturers prepared AI milliliters of the ith sort of tea, and jth taster can taste BJ milliliters of tea at once. Okay, so we are basically given two arrays A and B. What does those arrays represent? That AI represents that the ith sort of tea is available in AI milliliters, is the availability of the ith sort of tea, and the array B represents that BJ represents that the jth taster can taste BJ milliliters of tea at once. Okay, the tasting will be conducted in steps. So in every step, what would happen? In the first step, the ith taster tastes the ith sort of tea. Okay, and he would drink the minimum of AI or BI. Okay, so whatever, if less number of tea amount of tea is available, he'll drink all of them, or if he can drink whatever he can drink at once. Okay, so whichever is minimum AI or BI, that much would be drunk at once by the ith taster. Now, once that amount is drunk by him, AI also decreases by that amount. Okay, so the available amount of tea also decreases by that amount. So this happens in the first step, that the ith taster tastes the ith sort of tea. Then in the next step, what would happen? The ith taster tastes the I minus one sort of tea. Okay, and then in the next step, I minus 2th sort of tea is tasted by the ith taster. Okay, so likewise that would move until the until the step where every the last taster tastes the first tea. Until that we would move. Okay, so like you can see in this example, what we were given, like this is the first test case. Array A was 10 20 15, array B was 9 8 6. Okay, so this is array A. The amount of available tea is, okay, so this is array A, and array B is, this is 9 8. Okay, so this is 9 8 and 6. Okay, so this is array A, this is array B. So the first person, he can drink 9 milliliters at once, second person can drink 8, third person can drink 6 milliliters at once. And the first type of tea is available at the amount of 10 milliliters, second is available 20, third is available at 15 milliliters, that much is available. So in the first round of testing, what would happen? The minimum among 10 and 9, the minimum 10 and 9 is 9. Okay, so 9 milliliters would be tasted by the first person. So the amount that the first person has tasted, it goes up to 9, and the available amount for the first tea from 10, it's now only 1. Okay, minus 9. For the second tea, the minimum of 20 and 8. Okay, so the minimum of 20 and 8 is 8. So 8 milliliters would be tasted by him, and this available would reduce by 8, it would become 12. And same way for the third tea, minimum of 15 and 6 is 6. So 6 would be tasted by him, this would become 9. Okay, so you can see 1, 12 and 9, these are the remaining amounts for the second round. And every person would move one step ahead. So these three person, the first, second, third, they have now moved one step ahead. So this is the first person, second person and third person. The amount they have tasted is now 9 8 and 6. Okay, 9 8 6 is the amount they have already tasted. Okay, so in that second round of tasting, what would happen? The this first person has moved out, so he won't taste anything more now. Now the second person tastes the first tea, so minimum of 1, and the amount he can taste, 8, is 1. So he would taste 1 milliliter, this becomes 9, and the available tea becomes 0. The second sort of tea is available in a quantity of 12 milliliters, but the third person can taste only 6 at once. So minimum of 12 and 6 is 6. So he tastes 6 more milliliters, it becomes 12, and 12 becomes 6 is the available amount now. And this tea is not tasted by any person. Okay. Now, after the second round, what happens? The first person has tasted 9, second has tasted 9, third has tasted 12. So 9, 9, 12, and the amount they can taste is 9 8 6. and the remaining amounts are 0, 6 and 9. So 0, 6 and 9 are the remaining amounts. So now again, this third person is going to taste first. So minimum of 0 and 6 is 0, so he won't taste anything. 12 would remain 12, 0 would remain 12. And after this round, they all move ahead and the tea tasting finishes. So it finishes off with what amounts? 9, 9 and 12. Okay, so 9, 9, 12. First person tastes 9, second tastes 9, and third person tastes 12 milliliters. So our answer for this test case would be 9, 9, 12. Okay, I hope you understood what the problem statement is and what you need to find. So what you need to find is, for every person you need to find how much milliliters of tea that person tastes. Okay, so what would you do? Okay, like if you take this, let's say if you take this test case, what is happening? So this is your array A, this is your array B. Okay, so if you look, what is going to happen in the first step, this 3 milliliters would be tasted, this 13 would become 10, 4 would be tasted from here, 2 would be tasted from here, 1 would be tasted from here, likewise, and they all have tasted 3, 4, 2, 1. Okay, then they move ahead. Okay, so these would be the combination of tasting. So 4 would be tasted, it becomes 6, 2 would be tasted, it becomes 2, 1 would be tasted, it becomes 2, and their tasting also increases by those amounts. Okay, again they move ahead and this process continues. Okay, so what if you simulate this process and write your final answer like that? Okay, what would be the time complexity of that if you just entirely simulate this process? Now in every step you have to, like, in the first step there are 4 possible matchings, so you have to take the minimum of them and add them to your answer array or subtract from the remaining t amount. Okay, so 4 operations would be done in the first step. Then in the next step there would be 3 matching. Okay, so 3 operations would be done in the second step. In third step 2 operation would be done. In the fourth step 1 operation would be done. Okay, so if you have a like an array of size n, how much like time it would take? It would take n plus n minus 1 in the next step, n minus 2 in the next step, likewise up to 1. So which is actually n into n plus 1 by 2. So this actually is an order of n square thing. Okay, so if you just simulate this entire process, you would have n steps in total, and in every step you would require at max order of n computations. So that would take you an order of n square time complexity. But if you look at the constraints of the problem, n is up till 2 into 10 to the power 5. Okay, so the constraint states that n is less than equal to 2 into 10 to the power 5. So for this constraint, if you run something of order of n square, so n square goes 4 into 10 to the power 10, that would definitely not be executed in 1 second. So this would definitely give you a TLE. So what is the expected time complexity that you need to solve the problem in? So your expected time complexity for this constraints would be either you solve it in order of n only, or something like order of n log n you can go, or at the worst case you can go up till n root n. Okay, so these complexities would be accepted, but if you go something of order of n square, that would give you a tail. So now how do we reduce our time complexity from an order of n square to anything among these? Okay, so the first thing is what you need to observe in this. Okay, so if you observe what you like, if you are going step by step, then in every step you are like you are doing n matchings and n operations, n updations you are doing. So if you try to like compute those updations in some quicker time, that's what we need. So instead of looking at the problem like in every step what updation we are doing, let's say what you need to find, you need to form your final array which just represents that the first, second, third person, every how much tea the every person tastes. Okay, so if you look at this available tea, if you look at every tea, let's look at this first tea. Okay, what happens to it in every step? In the first step this is tasted by the first person. Okay, and this gets reduced to 10. Okay, what happens in the next step? for this particular sort of t only I am talking about, it get tasted by the second person, so it get reduced to 6. Okay, now what happens in the next step, third step, this tea is tasted by the third person, so he drinks 2 milliliters and this get reduced to 4. Now what happens in the next step, this is tasted by the fourth person, he drinks 1 milliliter of tea and this get reduced to 3. After that there are no persons, so it would end here, so 3 milliliters would remain. But what we needed to find is its contribution to this array, which represents the final amount of tea that every person tastes. Okay, so if you look this 13, 3 gets contributed here, 4 gets contributed here, 2 gets contributed here, 1 gets contributed here. Okay, what if you look at this 8? Okay, what is happening to that? For this 8, in the first step this second person taste it, so this 8 get reduced to 4. In the next step this third person tastes it, so this 4 get reduced to 2. In the next step this fourth person tasted, this 2 get reduced to 1. Okay, so what's the contribution of this 8 to our final answer? 4 is contributed here, 2 is contributed here, 1 is contributed here. Okay, same way you can look at every t. So in general what you can say, okay, let's say if this 13, instead of like let's say we had an array like this, array A was 12, 15, 10, 5, or array B was, let's say, 8, 3, 4, 15. Okay, then for the first person, first this guy would taste it and it becomes 8, 12 minus 8, 4. Then this person would taste it, it becomes 4 minus 3, 1. Then in the next step, this person can taste 4 milliliters, but only 1 is available. So only 1 would be tasted by it and it becomes 0. Okay, so for every t, we can see that from I, if you are looking at the ith t, then from I, there would be some people who would get a full tasting. Like for this case, here this person from this, like you can say, this person gets a plus 8, this person gets a plus 3. But after 8 plus 3, it's 11, only 1 is available. So this person only gets a plus 1. Okay, so you can say these two people got a one full tasting and this person got a partial tasting of whatever tea was remaining there. Now, if you look at this second sort of tea, for this it would be tasted by an amount 3 by the second person. Okay, so this contributes, like you can see, this contributes an amount of plus 3 this side. Okay, and it becomes 12. Okay, and then this person tastes 4 here, so this contributes a plus 4 here and it becomes 8. Now this person can taste 15 but only 8 is available, so you get a partial tasting of plus 8 here and this becomes 0. So for this person also you can see that these two people got a full tasting and this person got a partial tasting. Okay, so for this person also you can say that these two got a full tasting and this person got a partial tasting. Okay, so with this what you can conclude, okay, that for any I, like if you have an array A, for any I you can say that up till some index j you would get a full tasting, and then for the j plus 1th index you would get a partial tasting of the remaining amount. And how much amount would be remaining? It would be the amount tasted by these people. Okay, so this minus the amount tasted by these people, so 15 minus 7 is 8, so 8 would be tasted by this person. So like now can you say like that can you do this whole thing in order of n? So what we are going to do, that we'll go to every I. For this I, okay, now if you want to compute that what that optimal j is, let's say we have computed what that optimal j is, that for this I these two were the full testing, and so this I would call as the j, and this I would call as j plus 1, where we get a partial testing. Okay, or so if you can compute that j, then you can directly write that for all these people, if you can somehow update a plus 1, that number of full testing for these people. So in an array you can like update a plus 1, you can do using a difference array technique. You can update in a you can do a plus 1 in a complete range. So using a difference array technique in O of 1, you can do an updation that a plus 1, that complete testing has been done by these many people, one complete testing. And then for this jth person, you can calculate how much partial testing this person does. So in a different array which computes the amount of partial testing that every person does, in that you can update that 12 minus this sum. So this sum can be computed using a prefix array in order of 1. So 12 minus this sum, which is 11. 12 minus 11 is 1. So you add a plus 1 to the partial testing at this j. And how do you compute this j? This can also be computed if you have pre-computed your prefix array. Then from this index up till where do you go so that the sum just exceeds this 12? Okay, so that you can compute using an upper bound. Okay, so I'll explain you step by step what process we are doing. So if we have an array a and an array b. Okay, so if we are at any index I, we would maintain two arrays. One is the number of full testing. Okay, number of full testing that would be updated for every person, and the amount of partial testing. Okay, amount of partial testing that would be updated in another array. So we are going to maintain these two arrays, and what we are going to do is just for every I, whenever we are at this I. Okay, so we'll compute such a j using an upper bound in the prefix sum array. We can compute such a j so that the sum until that j, let's say we got this j, that means that the sum for these are less than or equal to this bi or ai. Okay, so the sum from first thing we are saying that the sum from I up till j is less than equal to ai. Okay, so we would compute such a j. Okay, so in our prefix array we can use an upper bound function to compute such a j so that the sum from I till j is just less than equal to I, the maximum j we can say. So then we would say that from I up till j minus 1, that from I up till j minus 1 we are doing a complete testing, a plus 1 to the complete testing, and for j we would do a partial testing. Okay, so in our complete testing, full testing array, from I up till j minus 1, we would do a plus 1. Now, how do we do this complete updation in O of 1? We do a plus 1 here and a minus 1 at this index j, and at the end when we take the complete prefix sum of that, we would get a plus 1 plus 1 plus 1 here, and this would become 0. Okay, so you know the difference array technique. So through the difference array technique, we would update this range from I till j minus 1. We do a plus 1 in this range. Okay, so this plus, actually instead of doing a plus 1 to every range, what we do is we do a plus 1 at I, and at j we do a minus 1. So finally when we do a prefix sum of this, we would get a plus 1 in this range, and this minus 1 would make it 0 for remaining range. Okay, so using a difference array technique, we do that. After that, for the jth index, what we need to do is this jth index should contain the partial testing that we have done. So how much partial testing is we have done? So the amount of partial testing that, let's say I'm telling x is the amount of partial testing that we do, that would be the this ai minus this sum. Okay, so that would be ai minus the sum from I till j. Okay, so this way we get the amount of partial testing, and at this index, at the jth index, we do a plus x. Okay, so this much amount we do update here. So for every index in order of 1 we are doing this updation, and in order of 1 we are doing this updation, and this j is found using a upper bound function which runs in order of log n. Okay, so for every I, once we do it, then what would be our final answer? Our final answer array. So our final answer for the ith index would be, for this full testing array, let's say whatever is the full testing of I, this multiplied by bi, because in every full testing the ith percentage bi amount of t. So this multiplied by bi plus the amount of partial testing for the ith index. So this we can say would be our final answer. So once we have computed this partial testing and full testing arrays, after that we can just compute this final answer in order of n by moving to every I, and this would be our final answer. So our overall time complexity for this computation in every ith step, upper bound was taking log n time, so our overall time complexity was n log n. Okay, so in n log n time we are doing this. I hope this logic is clear to you. So let's do a very quick dry run on one of the test cases, then we'll move to the code. Okay, so let's do a dry run on this test case only, or this first test case only, so that you understand what is happening here. Okay, so we have this array A and we have this array B. So this is index 1, 2, 3. First, we'll compute our prefix sum array so that we can use an upper bound there and calculate the things. So we take the prefix sum of this array B, so it would be 9. 9 plus 8 would be 17, and 17 plus 6 would be 23. So this would be a prefix sum array. Okay, and now we'll move to every index I. Okay, like let's say we are taking a zero based indexing only. In my code I'm taking zero based indexing, so it would be better if I do the dry run with zero based only. So in a zero based indexing, finally we'll compute, we have computed two things, the full testing array, okay, and the partial testing array. So the number of full testing and the amount of partial testing for each person. So for the first, when we are at the first index, that is for I equal to 0, what we would say that this 10 is contributed with a full testing to what all. Okay, so how do we compute that j so that the sum from here up till that is just less than or equal to 10? Okay, so in our prefix array we can see that if we take only this, then it is just less than 10, which is 9, and if we include this, then it becomes more than 10. So we take this j so that it becomes just more than 10, or j till j minus 1 it is less. Okay, so we'll take the upper bound of, okay, so at any I, okay, for the first index we didn't subtract anything. If we are at this index, then we are taking the sum starting from here. Okay, the sum starting from here, so this 9 needs to be subtracted. Okay, so we don't take the upper bound from 20, but upper bound from 20 minus the sum up till here. Okay, I hope you understand that what we needed to do is we need to make sure that the sum from I up till j, this sum is just greater than equal to ai. We need to find such a j. Okay, so this sum from I up till j can be written as prefix sum j minus prefix sum I minus 1. Okay, this should be greater than equal to ai. Okay, we have pre-computed our prefix sum array. So I hope how you write for sum from I to j. This should be greater than equal to ai. So we can say that we need to find such a j so that the prefix sum till j is greater than equal to ai minus prefix sum till I minus 1. Okay, so this would be a constant value for I. So we can say that we take the upper bound from this. Okay, like you can take this equal to sign or not take this equal to sign, because it would not affect. You can either take the upper bound or the lower bound, both would be the same, because for the equality case, when you are taking exactly this much, so like let's say you are taking exactly this much, so you can include this 8 in the full testing also, or it can be included in the partial testing also. It won't affect your answer. So you can take either upper bound or lower bound. I hope that is clear. Both can be done. So let's say we are taking strictly increasing and we take the upper bound, then this prefix j should be greater than ai minus prefix I minus 1. So we take the upper bound of this in the prefix array. Okay, so in our prefix array we take the upper bound of ai minus prefix sum up till I minus 1. Okay, so once we have computed this, okay, this would give us our required j. Okay, so for this particular case, for the first index we get j equal to 1. So for I equal to 0 we get j equal to 1. So for this we would update from I up till j minus 1. So in full testing we do a plus 1 here from I up till j minus 1. So at j we do a minus 1. So this way we would be updated when we finally do the prefix sum of that. And for our partial testing, it would be how much is our x. Our partial testing is the ai minus the sum from I till j or j minus 1. Okay, so that sum you can see this is 9. Okay, so 10 minus 9 here in this case it would be 10 minus 9 1. So one full testing would be done here. So a plus 1 here. Now when we move to I equal to 2 or I equal to 1, then what would happen for 20? Our j would just exceed here and go like 8 plus 6 is still 14, which is still less than 10. So our j would be like one more, it would be 3. Okay, we have index from 0 1 2, but our j would be here. Okay, so we get j equal to 3 here. So we do a complete testing to both these indexes. So we do a plus 1 here and a minus 1 at this index. Okay, so that you get a plus 1 in this complete. And for partial testing we don't do anything because there is only full testing. For I equal to 2, what happens? For I equal to 2 we have 15. So for 15 you can see that only this 6 will do a full testing, after that nothing else. Okay, so we do a plus 1 here and a minus 1 one more here and nothing in the partial testing. Okay, so our full testing array becomes plus 1 here, so 1 plus minus 1 plus 1 becomes 0, plus 1 is 1, and this is minus 2. That index actually doesn't matter. To this we do a prefix sum. So when we do a prefix sum it becomes 1, 0 plus 1 1 and 1 plus 1 2. So these are the amount of full testing done, and our partial testing is, you can see, 0 1 and 0. Okay, so partial testing array is 0 1 and 0. So our final answer, what would that be? So that you can see that the final answer is number of full testing into bi plus partial testing. Okay, so for the first index there is one full testing, so 1 into bi is 9, 1 into 9 is 9 plus partial testing is 0, so it's 9. Then 1 into the array b1, b1 is 8, so 1 into 8 plus 1 partial testing. Okay, so it's 1 into 8 plus 1, which becomes 9. Okay, so a 9 here, and there is 2 full testing and 0 partial testing. So 2 into 6, it becomes 12. 12 here. So our final answer is 9 9 12. You can see that for this test case our final answer was 9 9 12. I hope it is clear to you now. So we'll look at the code. Okay, so in our code, what we are doing, we take the input. First of all, I'm using a hash defined int long so that whatever you are seeing as int is actually long. Okay, because when we are doing a sum up till n and our n is 1e5, ai is up till 1e9, so this sum may exceed the integer range, so you need to use long here. So I have done a hash defined int long so that all my int is converted to long. Okay, and you have to write a int 32 main so that you cannot convert this int to long, otherwise it will give an error. So here I have taken the t test cases and I'm running the solve function for every test case. Now for every test case, what I'm doing, I take the input, this is the input part, and then the array a and b. After that I compute my prefix sum array. So this prefix I is prefix I minus 1 plus bi, so I compute the prefix sum of array b. After that, this count array is the count of full testing. Okay, so this is what I'm computing in this count array, and my array is my final answer array. Okay, so the partial testing would be updated in my answer array, and finally I'll just multiply my count array with bi, update it in this array only, so it becomes my final answer. Okay, so initially I would compute the partial testing in my answer array, and finally I would add bi into count to get my final answer. So for every I, what I do is I compute this x ai plus prefix sum I minus 1. So what I had explained you there, sorry. So what I had explained you there is, what you need to do is you need to take the upper bound of ai minus prefix sum of I minus 1. So this is computed in my array x. Okay, so in my array x, I take ai plus prefix sum of I minus 1, and I take the upper bound of x. Okay, so minus prefix dot begin, because this returns, upper bound function returns an iterator, so I subtract dot begin to get the index j. Okay, so once I've got the index j, if this j is less than equal to n, then I update that in my answer array. I update the partial sum. Okay, I have taken one based indexing here. What is that? Okay, in while explaining the dry run, I had explained using zero based indexing, but it is one based indexing here. So when j is less than equal to n, if it is in the range up till n, it's not n plus 1, then I update my answer array as how much I update to my partial sum. What is updated to the partial sum is ai minus sum from I till j minus 1. Okay, and this sum from I till j minus 1 can be written as ai minus, this sum can be written as prefix sum of j minus 1 minus prefix sum of I minus 1. Okay, so this is actually ai minus prefix sum up till uh, ai, this minus minus become plus prefix sum I minus 1 was computed here, ai plus prefix sum I minus 1. Okay, so this was actually plus only here. Okay, I hope you understand. So this answer j is updated as x minus prefix sum up till j minus 1. After that, this, so you can understand here what it was. So this ai plus prefix sum, this whole thing becomes x, this I was taking as x, minus this is the actual what is gets added to my partial sum. Okay, so x minus prefix sum j minus 1. Okay, so these things you can like compute and write. So this way I'm updating my partial sum. After that, this way I'm updating my complete sum. So I gets a plus 1 and j gets a minus 1. So I update the range from I till j minus 1. I do a plus 1 there. Okay, so finally when I do this prefix sum in this count array, I get the actual count of the amount of full testing done. And in my answer array, what I do is I add count I into bi. This way I update my answer array. So initially my answer array was storing the partial sum. In the partial sum, I updated that I know the formula that my answer I is this partial sum plus complete sum into bi, number of the count of complete sum into bi. So in my answer array, I updated the count of complete sum into bi. So this way I got my final answer, and I'm just printing it for every I. Okay, and I print the next line. So I hope you understood the code. If you analyze the time complexity of this is the input part. After that, this prefix computation is taking an order of n time, and then I'm running a loop n times. This upper bound function is actually taking an order of log n time. Okay, and these are order of 1 operations. Okay, so this complete loop is taking n log n time. Okay, and this is an order of n operation, and this again is an order of n time. Okay, so overall you can see that n log n is the worst time in this, so we can say that overall time complexity is order of n log n. Okay, and what would be my space complexity? It would be, I'm just using two vectors, array a and b, and this prefix sum vector of size n, and these vectors are also of size n. So all my vectors are of size n, so my space complexity would be order of n. Okay, so I hope this problem is completely clear to you. It was more about understanding this difference array concept that we are using here, along with this upper bound on the difference array. and like it was a combination of using a prefix sum technique and the difference array technique both together in a problem. So that was nice, and I hope you liked the explanation of this problem. Thank you very much for tuning in.